Welcome back to the Mechanics of Solids lecture series. In this next series of videos, we'll solve for examples for bending stress and bending moment of inertia in beams. The lesson objectives are to be able to compute normal stresses in a beam due to bending. In order to do this, we'll often need to locate the neutral axis and compute the bending moment of inertia for general cross-section shapes. The first example that we'll look at is based on an illustration from Mechanics of Materials by Timothy Philpott Wiley, 3rd edition. It's an upside-down channel section. For this section, we're asked to compute the centroid, the moment of inertia about z, and the normal stress on the bottom of the flanges due to an applied moment of 1.05 kilonewton meters. So first, we'll start out by summarizing what we're asked to compute. Find the centroid, which I call y bar, in units of millimeters, the bending moment of inertia, Iz, and should be given in millimeters to the fourth, and then sigma x at the bottom, and sigma x is a stress, so we'll want to compute it in units of megapascals. Let's start out with the centroid. Remember, the definition of a centroid is y bar equals the sum of a sub I times y sub I over the sum of a sub I, or the total area of the section. This formula has been designed to deal with breaking our section down into discrete rectangles and adding the contributions for each rectangle. So for the channel section, we can see from the illustration that it's broken down into section 1, which is the top web, section 2 and section 3, which are the side flanges. And the contribution of each of those will go into the calculations indicated there. So in order to do these calculations, it's most convenient to summarize the calculations in a table. So I'll start by creating a table over here, and I'll add the contribution of section 1, 2, and 3 in the table. And in the various columns, I'm going to tabulate for each section its area in millimeters squared, its y sub I value in millimeters, and the product of the two, a sub I times y sub I, which would be millimeters cubed. In the end, I'll want to sum the areas and the a sub I times y sub I term. Okay, so start out adding together these contributions. Let's start with section 1, the top web. The area of that section is equal to its width, 75 millimeters, times its thickness, 6, which is 450 millimeters squared. Its y sub I should be the value to the centroid of that section from a reference axis. So we need to define a reference axis. Label it here, reference. I'll take the bottom as the reference point. So y1 would be the value from the reference up to the centroid of the web on the top. I'll label it y1, or excuse me, y1. And that value we can compute as 40 millimeters, which is the total height, minus 3 millimeters, which is half the thickness of section 1. So it would be equal to 37 millimeters. Okay. Next, let's add the contribution for section 2 and section 3, which should actually be identical. The area of each of those sections is equal to its height up to this line here, which would be 40 minus 6, the thickness of the web. So 34 times thickness, 34 times 6, equals 204. And it's the same for both 2 and 3. The y sub I value, y2 and y3, is the distance from this reference up to the centroid of each of those sections. Label that y2 equals y3 equals, would be 34 divided by 2, or 17. So we can mark that as 17 for each of those. Now the third column we said is the product of the area and y sub I for each section. So 450 times 37 is 16,650. 204 times 17 is 3468. And I'll bring that down. And then I'm going to add the areas in the first column. And the sum is 858. I'll add the a sub I, y sub I values in the third column, and that sum is 23,586. Now I have the numbers I need to compute the centroid. Y bar equals sum of a sub I times y sub I, which is the third column, 23,586 millimeters cubed, divided by the sum of the areas, which is the first column, 858 millimeters, and this computes to 27.49 millimeters, which, as we said earlier, is already indicated on the section, so our calculations confirm. Note that the centroid location is 27.49 millimeters from the bottom or reference axis. From the top, it would be 40, the total height, minus 27.49, which is 12.51. And both of those numbers might be useful for computing peak stresses. So we'll continue this example in the next video.